Good morning, students. I am here with the second session of laws of motion, that is types of frames of reference. So before knowing about the types of frames of reference, let us know some of the terms related to this chapter. So you come across the word particle often, frequently throughout this chapter. So what is meant by particle? A particle is a piece of matter having no linear dimensions but only have a position. So particle, it is a piece of matter having no linear dimensions, means it does not have any length, breadth or thickness, but it will have only position. Mass, it is a measurement of quantity of matter. So you come across the word event frequently in this chapter. What is meant by an event? Event is anything that occurs suddenly, which happens suddenly or instantaneously at a point in the space. And we should also remember that event, it includes the information about both position as well as time, where it had happened and when it had happened. Both the things are to be known when we define an event. So observer, who is observer? Observer is a person or an equipment which can locate, record, measure and interpret an event. So observer may be a person or may be a machine or an equipment which locates, records, measures and interpret an event. So like this we can define some of the terms which you come often in this chapter. Next is types of frames of reference. As we have discussed in the last class, frame of reference is a coordinate system attached to the object of reference with respect to which we can locate the exact position of an event, or we can describe the motion of any event or particle. So the simplest form of the coordinate system, as we have discussed, is the Cartesian coordinate system, with the help of which we can define or we can describe the translational motion. But there are other types of coordinates also are there, such as curvilinear coordinates, polar coordinates, spherical polar coordinates, with the help of which we can describe the motion in a curved path or rotational motions. And it is very convenient for us to use the Cartesian coordinate system. Why is it so? Because we can convert all the other types of coordinate systems into this translational coordinate system, translational coordinate axis, such as x, y and z can be written in terms of r, theta and phi. So like this, and it is very convenient for us, and we are very familiar with the Cartesian coordinate system, and we know how to measure the velocities and quantities related to motion of an object with the help of these Cartesian coordinates. So that is why we make use of the Cartesian coordinates in most of the problems related to motion. Now, what are the types of frames of reference? There are two types of frames of reference: inertial frame of reference and non-inertial frame of reference. So inertial frame means, inertial frame of reference is that frame of reference in which Newton's laws of motion holds good. So as we know, Newton's laws of motion states that unless until compelled by any external resultant force, a particle will remain in its state of rest or a state of motion in a straight line. And the second law, it gives the expression for the force, that is F is equal to m into A. So in order to produce a definite amount of acceleration in an object, a definite amount of force has to be applied. Without the application of force, no acceleration is observed. So this is the Newton's statement. Now, inertial frame of reference are those frame of references in which these Newton's laws holds good. The examples for such frames are rest frame and frame moving with constant velocity. So you should remember the examples for inertial frames of reference are rest frame and frame moving with constant velocity. Now there are another kind of frame of reference is also there. They are non-inertial frames of reference. So it is exactly opposite to that of the inertial frame of reference. Here in non-inertial frames of reference, Newton's laws of motion does not hold good. How do we say that Newton's laws does not hold good in non-inertial frames of reference? Here, without the application of any resultant real forces, the particle appears to be accelerated. So that is why we can say that in such a frame of references, Newton's laws does not hold good. The examples for such frames are accelerated frame and rotating frame. So you can understand. Here we have two frames of reference, S and S dash, and S dash is moving with constant velocity v with respect to S in the positive x direction. So these two are the inertial frames of reference. So this is a common example we can take usually in order to find out the transformation equations. So these two are called as inertial frames of reference. If the particle P is observed by the observer in S or S dash, so the particle P, if it is at rest with respect to S dash, the particle P appears to be moving with velocity v with respect to the observer in S. But no force is experienced or no acceleration of the particle P is observed with respect to these two frames unless until force is applied on them. If force is applied on this particle, then only both the observers can see that the particle is accelerated. Otherwise, they won't. So that is how we can say that Newton's laws holds good in the case of inertial frames of reference. Now here you can see one more example of two frames of references again. Here the frame S is at rest and the frame S dash is moving with an acceleration of A with respect to the first frame S. Now the thing that is observed is entirely different here. The person who is in the frame S dash, he observes the particle P to be accelerated in the opposite direction with an acceleration of minus A. So how it is possible? Even though no external force is applied on particle P, this person is seeing this particle to be accelerated in the opposite direction. So that is how the observers in the non-inertial frame could see the acceleration of the particles even though no real forces are acting on them. Such a forces are known as pseudo forces and such a frames of references are known as non-inertial frames of reference. Now, the examples for non-inertial frame, as I have told, it is an accelerated frame and the rotating frame. Both are the examples for non-inertial frames. So here you can see this truck is moving in a curved path. If a person is freely sitting in the truck, so while taking the curved path, he feels the force outside or away from the center of the curve, isn't it? Or else we can see that here there is one box which is kept at this side of the truck, but when this truck take the turn, this object will move at the other side of the truck. So this is because of the throw which is away from the center, which is called as centrifugal force. So even though no actual force is acting on it, it is feeling the force or experiencing the force because of the frame of reference, that is rotating frame of reference. So such a frames are called as non-inertial frames of reference. You might have experienced that when the bus suddenly starts, when the bus you are sitting in is suddenly starts, you will feel you will thrown back. You will feel that you are thrown back. Why is it happens? Because no one have thrown you back, but you are feeling that. Why it is so? Because when the bus starts, its velocity changes, means hence it possesses some acceleration. Now your bus has become a accelerated frame of reference, where even though no external force is applied, the force is experienced, isn't it? So that is how you experience pseudo forces or fictitious forces which are not real in the non-inertial frames of reference. So that is how it does not obey the Newton's law of motion. Now let us move towards the next topic, that is transformation equations. As you all know that there are several types of frames of references, and the motion, if it is observed from one frame, that would be different from the other frame. Now if you want to translate or transmit all the coordinates of one frame into another, if you want to write the equations for a motion for all the systems with respect to each other, then we need certain equations relating the coordinates of the two systems. They are called as transformation equations. So how you are going to define transformation equations? The equations relating the coordinates of two frames are known as transformation equations. Here you can see there are two coordinate systems, s and s dash. So the xyz coordinates of the frame S are x, y and z, and the coordinates of s dash are x dash, y dash and z dash. Now how to write x, y, z in terms of x dash, y dash and z dash? So the equation which relates the corresponding coordinates of the two systems, any two systems, are known as transformation equations. So here you can see an event P whose coordinates are x, y, z and t. X, y, z are the position coordinates and t is the time coordinate with respect to the frame S. And x dash, y dash, z dash, t dash are the position as well as time coordinates with respect to the frame S dash. Now how to write x dash in terms of x? How to write y dash in terms of y? So the equation which relates these coordinates of the two systems are known as transformation equations. I am going to consider here a very simple example. Assume that s and s dash both are at rest. Here frames s and s dash both are at rest. Now the x coordinate of the point P or event P with respect to SB capital X. Now the x coordinate of the same point P with respect to S dash be taken as x dash. Now how to give relation between these two? For that we need to know the distance, this distance, that is the distance x, distance in the x direction, how much it is, how much this system is for, how much this system is away from this system. So there is a difference in the x-axis only. So how much is the difference? L. Then we can write x in terms of x dash as x is equal to x dash plus L. So this equation is called as transformation equations. So here what we are doing? We are relating x dash and x. And there is no change that is observed along y and y dash. Both are same only. In the same manner, z is equal to z dash and t is equal to t dash. Means the event is observed, the time of the event that is observed will remain same for both the frames of reference, as both of them are at rest. Now, what are Galilean transformation equations? So, of course, they relate the coordinates of two systems, but how those two systems be those two systems must be inertial frames. Then only the equations are called as Galilean transformation equations. The equations relating the coordinates of one inertial frame to another inertial frame of reference is known as Galilean transformation equation. So here both of the systems must be inertial frames. Then only the transformation equations are called as Galilean transformation equations. So here you can see that, so if both of the frames are at rest, then the equations are called as Galilean transformation equations. If both of the systems are moving with some constant velocity, so there it is observed that both of them will have some relative velocity, isn't it? At that time also the corresponding equations relating the coordinates of the two are known as Galilean transformation equations. And if one is at rest and another is moving with some velocity in a particular direction, then also the equations which relate the coordinates of the two are known as Galilean transformation equations. So here in general we are considering, in order to obtain the in order to derive the Galilean transformation equations, we are considering one frame at rest and another frame moving with velocity v along the positive x direction. Now assume that there are two frames s and s dash. S dash is moving with constant velocity v with respect to s in the positive x direction, and assume that at a time t is equal to 0 both of these frames are coincided, isn't it? They start from time t is equal to 0. So hence we can say that t is equal to t dash. Why? So both of them at time t is equal to, both of them start from the origin O, and after some time this s dash moves with velocity v. After some times it reaches this point, isn't it? Hence we can say that the time coordinate for both of them is same. Now how to obtain the relation between x and x dash? Now how to obtain relation between x and x dash? For that again we need to obtain this distance. So how to obtain the distance? This distance, we know the velocity of the frame is v, and the time that is lapsed is t. Hence the distance that is covered after time t would be equal to v into t. Hence this distance would be taken as vt. Now you can definitely give the relation between these two. How? Here we can write x equal to, that is from here to here, x equal to vt plus x dash, x equal to x dash plus vt. So this is the Galilean transformation equation which is relating the x coordinate of the two systems. Now what about y and y dash, z and z dash? Because the motion is only along x-axis, we can take there is no change in the y coordinates or z coordinates. The what you call coordinates of s and s dash will remain same. Y and z coordinates for s and s dash will remain same. So hence we can write y is equal to y dash, z is equal to z dash, and of course t is equal to t dash. These are called as Galilean transformation equations. So that is how we can derive the Galilean transformation equations. So Galilean transformation equations are those equations which give the relation between the coordinates of two inertial frames of reference, that you have to remember. So students, in this class we have learned that what is meant by an inertial frame of reference. So it is the frame of reference in which Newton's laws holds good. What are non-inertial frames of reference? These are the frames of reference in which Newton's laws does not hold good. And we also came to know that what are transformation equations and what are Galilean transformation equations. So after learning all these things, I'm going to put you all a question: whether the earth on which we live is an inertial frame or a non-inertial frame. So with this, I am going to end the second session. Thank you.